everyone. So, in this lecture, I will talk about classifier ensembles, a machine learning technique for combining multiple classifier models to produce a classifier that is much more powerful than any of its component models. So, the idea of combining together classifiers has been around since the late 1970s, particularly when John Tukey of the uh, Cooley-Tukey Fourier transform algorithm, okay, the same person, Tukey there, described a combination of two regression or linear regression models. But it was only in the 90s, late 90s, that substantial progress was achieved in this area, especially when Shapir and Freund laid the foundations for boosting algorithms using ideas from learning theory, specifically that of PAC, or probably approximately correct learning. Now, instead of covering each of the many different instantiations of what constitutes a classifier ensemble, today we will only discuss the important notions and basic principles in order to understand the growing literature on this subject. I will introduce the rationale for combining several models, and then we'll proceed to discuss the two general classes of ensemble models: boosting and bagging, and different methods for combining the outputs of the classifiers. And finally, we'll have a worked out example for a boosting classifier called AdaBoost. So again, the rationale for putting together different classifiers is so that we can exploit their individual advantages in order to achieve an overall performance that is better than each of the different classifiers considered separately. So, is there wisdom? Is there really such a thing as wisdom of the crowd? Around 2 centuries ago, an English statistician by the name of Francis Galton, well, he was not just a statistician, he was also a psychologist, a sociologist, geographer, meteorologist, inventor, etc., or simply put, a polymath whose knowledge spans many fields and excelled in all of them. So I was saying, Francis Galton made the following experiment. While visiting a livestock fair, Galton was intrigued by a simple weight guessing contest. The visitors were invited to guess the weight of an ox. Hundreds of people participated in this contest, but no one managed to guess the exact weight, which was 1,198 pounds. But what surprised Galton was that the average of all the guesses came quite close to the exact weight, 1,197 pounds. So it's just off by 1 pound. So this story of Galton has been has been repeated many times, countless times, to demonstrate the wisdom of the crowds or collective intelligence. Now, about half a century before Galton, the Marquis of Condorcet formulated the Condorcet's jury theorem, which states that if a member of a group of voters is more likely than not to make a correct decision, that means that each member of a group of voters will have a probability of greater than 50% of being correct, each one of them. The probability that the majority vote of the group is the right decision. And this probability increases as the number of members increase. So to be a little bit more formal, we have the following. A jury of voters needs to make a decision regarding a binary outcome, which is, for example, to convict or not a defendant. If each voter has a probability P of being correct, and the probability of the majority of voters being correct is L, okay, meaning majority vote, then if P is greater than 0.5, okay, which means each of the voters in the jury, each of the member of the jury is correct, or has a probability of being correct greater than 50%, and this implies that L, the probability, will be greater than that P. It's rather obvious, okay? But the second one is more interesting, that for all P greater than 50%, meaning all voters having a probability of being correct greater than 50%, it could be 51%, it could be 50.5%, as long as it's greater than 50%, as L then L approaches 1 as the number of voters approaches infinity, meaning the probability of being correct approaches 1. Imagine, approaches 1. Probability approaches 1 as the number of voters approaches infinity. As the number of voters increase, the probability of the entire jury being correct approaches 1. So, going back to this condition, P greater than 1. Now, what happens if P is less than 1? That some of the voters will have the probability of being correct less than 50%. Okay, then having more voters will make things worse. In fact, the optimal number in that case is just 1 voter. Okay, so again, if the probability of each voter is the probability of each voter being correct is less than 50%, meaning it's likely that the voter is going to be wrong, okay, then having more voters in a jury will make things worse. It's better that it's just one person making that decision. So again, these ideas have been cited many times by political theorists and philosophers as a justification for democracy. Again, I'd like to remind you of the basic assumption here. The basic assumption that all voters with special emphasis on all, are more likely to be correct than not. Meaning, all of the voters, all, must have that probability greater than 0.5 of being correct. Otherwise, we cannot avail of this theorem. We cannot cite this theorem properly and support the so-called wisdom of the crowd. So this theorem has two major limitations. First is that there are only two possible outcomes. So that's one limitation, two possible outcomes. And that in the assumption that the votes are independent. That the votes are independent. So if the voters try to influence each other, then again, you cannot cite or quote or exploit this theorem. Then in 2004, is an author who published the book The Wisdom of the Crowds, Why the Many Are Smarter Than the Few, and How Collective Wisdom Shapes Business, Economies, Societies, and Nations. So basically, the author was saying that the aggregation of information from several sources would result in decisions that are often superior to those that could have been made by any single individual or even experts. So that's his, his thesis in this book. However, he also says that not all crowds are wise, by the way, since they may have the same crooked or dishonest motivations. No? So, like a mob is also a crowd. No? So, but they're behaving in the same way, and they're behaving irrationally. And again, also another example would be the greedy investor of a stock market bubble, and this happened in in 2007, I think. So this stock market collapsed because of some greedy investors who want to take advantage of the situation. So not all crowds are wise. So what's the criteria for the crowd to be wise? One, diversity of opinion. So these ideas are from the book of this guy. Number one is diversity of opinion. Each member should have private information, even if it is just an eccentric interpretation of known facts. Okay, so like for example, the stock market. Some stock market, so some example of this eccentric interpretation. So some stock market traders look at the moon to guide them in their decision to sell or buy stocks. So you might think, these guys are crazy. So why look at the moon? Why the moon? Oh, this seemed to be eccentric. Eccentric way of viewing things. However, it's actually a paper or several papers. If you go to Google, and how come it does not appear here? It's probably pushed down. But anyway, I will correct it in the slides that I will give you. There's a citation here which says that. That apparently eccentric interpretation is actually an intelligent way of looking at things. Why? Because in particular, a full moon would reflect a full moon increases the tendency of people to feel depressed or sad. and because of that, they might stay out of the stock market, or at least on that day of the full moon, and wait to sell their stocks due to this full moon at a later date. So, that, in other words, the full moon actually brings stress to the investors. And also, the opposite happens when there's a new moon, which is supposed to bring calmness. No? So, that apparently eccentric interpretation um, of nature influencing our decision making actually is based on some sound scientific facts, no? that that the moon would tend to influence our tendency to be depressed or to be calm. So, okay, that diversity of opinion is actually needed. No? So, diversity is important. It's very important. Second, independence. It's another condition for the crowd to be wise. The members' opinions are not determined by those around them. This is very important because, like in a mob is a crowd, but they think in the same way. So there's no diversity. Well, the opinions are of the members are there's no diversity in the first place, but they're not even independent. So the members' opinions should not be influencing each other. So, well, election, for example, there's fake news, there's paid advertisement, or walls, or worse, trolls, vote buying. So these try to, try to influence the voters' opinions. So, and affect independence, so that now the crowd is no longer considered to be wise. Then decentralization. The members are able to specialize and draw conclusions based on local knowledge. Then finally, aggregation. Some mechanism exists for turning private judgments into a collective decision. For example, majority voting. So it's just an example. It's just the only way, but it's actually the most common way to aggregate judgments in order to form a collective decision. Now we will use some of these ideas to improve the performance of our machine learning algorithms. And we will discuss today a class of machine learning algorithms called ensemble classifiers based on these different notions that we have discussed. Let's first define some terms. This is something that you already know, the training set. The training set is a set of instances whose labels are known. Okay, so we know this. Then inducer. The inducer is an algorithm that constructs a model. So this is a new term for us. This basically corresponds to the notion of classifier that we have studied so far. So all the classifiers that we have discussed so far, they're now going to be called today inducers, just for today. Okay, for this, when talking about ensemble, the classifier that we have learned before is to be called, supposed to be called inducers, not classifiers. So we will call the A and N the artificial neural network, the Bayes classifier, naive Bayes classifier, and all the other classifiers that we have studied and we will study in the future as inducers. When we're talking about, of course, about ensembles. And the classifier, on the other hand, is an instance of an inducer for a specific training set. So therefore keep that in mind. When we say classifier here, it's not the same as the classifier that we have studied before. It's just an instance of an inducer. The inducer is the same notion as the classifier that we have learned in the past. Okay, so take note of the change in terminology. Classifier here is not the same as the general term classifier. And the goal is to weigh several individual classifiers and combine them in order to obtain a classifier that outperforms every one of them. So let's have some more definitions, but this time more precise. Training set. A training set is a labeled data set used for ensemble learning. More frequently, the instances are described as attribute value vectors. So attribute value vectors. So this, when you hear the word attribute, that's basically a term that's used in statistics. Okay, but in machine learning, the term that's used is features. So there seems to be a difference. Well, there is in fact a difference between statistics and machine learning in the way they call things. So attribute is the same as features. Then let A denote the set of input attributes or features, if you want, containing n features or attributes. So these are the features, A1 up to AN. That's A. And Y to represent the class variable or the target attribute. Then we have the Bayes inducer, which is an induction algorithm that obtains a training set, informs a classifier that represents the generalized relationship between the input attributes and the target variable, target attribute. Let I represent an inducer. We use the notation M equals I of S for representing a classifier classifier M which has been induced by an inducer I on the training set S. In other words, you have an inducer, for example, Bayes classifier, like the spam filter classifier that you made. Okay, that's your I. Now that's in today's lecture we'll call that a naive Bayes inducer. Now that naive Bayes inducer, when you train it on a specific data set, like the data set that I gave you, now becomes a classifier. And we will call that classifier M. Okay, so that's your Bayes inducer. Then you have diversity generator, which is responsible for generating the diverse classifiers. And then combiner. The combiner is responsible for combining the classifications of the various classifiers. In other words, each of the classifiers will give their own respective results or votes, classifications, and then the combiner will aggregate them into just one result, which is the overall result or overall classification of your entire ensemble. Now we will distinguish between two frameworks for building ensembles: the dependent and the independent frameworks. In the dependent framework, the classifier output is used in the construction of the next classifier, often to take advantage of the knowledge generated in the previous iterations to guide the learning in the next iterations. That's the independent framework, which we shall discuss shortly. In the independent framework, each classifier is built independently and their outputs are combined. Again, we will also talk about this in the next slides. Now let's tackle the dependent framework first. There are two main approaches for this framework: the incremental batch learning and the model-guided instance selection approaches. For the first one, the classification produced in one iteration becomes prior knowledge to the learning algorithm in the following iteration. So you have a learning algorithm that uses the current training set together with the classification of the previous classifier for building the next one. And the classifier constructed at the last iteration is chosen as the final classifier. And the second one, model-guided instance selection. Here, the classifiers that are constructed in the previous iterations are used for manipulating the data set for the following iteration. So it's described by this diagram here. So you have your training set, and you have what is called a data set manipulator. It's basically chooses a portion of your data set. Okay, so this training set is partitioned by your dataset manipulator and produces dataset 1, which is just a subset of your training set here. Then this dataset 1 is going to be used to train the inducer 1, the first inducer. So we know that when you train an inducer, what comes out is a classifier. So we now have a classifier here. And that classifier is passed on to the classifier's composer here. And then at the same time, the output of this, the results rather of the first classifier will be used by the dataset manipulator to create the second dataset. So the dataset manipulator need to take in some inputs from the results from the first classifier. So it has to actually see what were the data points that were not correctly classified by classifier 1. What were the data points that were correctly classified by classifier 1? So that would be those would be your inputs to your dataset manipulator, this one here. And then based on this, it will again take a section of the training set, a subset here of this, and that would be the dataset 2, which will in turn produce classifier 2, which will again be stored by your composer. And again, the output here, the results of the classifier 2 for dataset 2 will be used to create the third, fourth, up to the tth classifier. So what we have here would be t different classifiers, classifier 1, 2, up to t. Now this this classifier composer will use these classifiers to label the different unlabeled features and produce hopefully a good predicted set of labels. And the performance of this overall composer would be better than any of these different T classifiers. So that's the idea. Now, some more terminology. Weak learner. What is a weak learner? A weak learner is an inducer that is only slightly correlated with the true classification. So when we say slightly correlated with true classification, this basically means that is slightly better than random guessing. We're talking here about a binary classification, 0 or 1. Okay, just two classes, spam or ham, or convict or not convict, or uh, patient is sick or not sick of COVID, that sort of thing. Just two binary outcomes. So here, a weak learner is is an inducer that is slightly better than random, than toss coin. Okay, 51% for example. Okay, maybe 60%. So examples of this of weak learners are decision trees, perceptrons. Okay, not multi-layer perceptron, but perceptrons. A strong learner, on the other hand, is an inducer that is arbitrarily well correlated with true classifications, meaning very high accuracy. Examples of that would be your ANN, artificial neural networks, or the SVM. So, so for one class of classifiers, we need a weak learner. Now, model-guided instance selection. So there are two main classes of ensemble classifiers. Boosting, well actually this is the second type, sorry. I'm talking about the second type. For the second approach, the model-guided instance selection, okay, there are two main algorithms that are very similar. One is called boosting. It's also termed arcing, which stands for adaptive resampling and combining. So this term is rather old. The more modern term is called boosting. It's a general method for improving the performance of a weak learner. This works by repeatedly running a weak learner on various distributed training data. Now, the classifiers produced by the weak learners in this model-guided instance selection are combined to form a single strong classifier. So, many weak learners, slightly better than random, could actually, when combined properly, give you a strong classifier that is as strong or even better than than your ANN or your SVM. So we're talking about this method, okay, the model-guided instance selection process. Another example of that is called aid the boost or adaptive boosting. This aid the boost focuses on patterns that are harder to classify. In other words, going back to this diagram here, so when the first inducer produces the classifier, it's of course evaluated on some validation set. Now the validation set will actually tell you which ones are not properly classified by classifier 1. And these misclassified ones will be given emphasis by the second classifier. So the second classifier therefore should be focusing on those examples or those parts of the data that's poorly classified by classifier 1. So what classifier 2 will be doing is to pay attention to those classifiers, the data points na mahina yung classifier 1, and similarly for all the rest. So together, they will try to help each other, one another, to come up with the best decision. So that is the idea. It's like people. So when you form a committee, don't choose members who think exactly the same way. So it's useless. Better to just, if that's the case, you just get one, and the way you think in the same way. So choose people who think differently, who will be looking at aspects of the same problem differently, so you could come up with a good decision. Now, the amount of focus for AWS is quantified by a weight that is assigned to every pattern in the training set. And initially, the same weight is assigned to all the patterns. So we will have an example of this at the end, so this will be clearer later on. And in each iteration, the weights of all misclassified instances are increased, while the weights of the correctly classified instances are decreased. So in other words, the next iteration, the next classifier now will be focusing on the misclassified instances, misclassified by the previous classifier. So that way, the weak learner is going to focus on the difficult instances of the training set by performing additional iterations and creating more classifiers. Then another weight is assigned to every individual classifiers. Higher weights are given to more accurate classifiers. And the weights are used for the classification of new patterns. So what we have here is an iterative procedure. The boost is an iterative procedure that will actually produce a series of classifiers that complement one another. And it has been shown that AdaBoost approximates a large margin classifier such as the SVM. So again, it has been shown that AdaBoost approximates a large margin classifier which is such as the support vector machine, which we will learn next meeting. Now, the other programming assignment, PA2B, is actually a comparison of AdaBoost and SVM, so that you will see for yourself that this is true. Okay, so imagine weak learners with just slightly better than random guessing put together in an ensemble can actually beat the SVM. Beat or almost approximate, I won't tell you the answer, so find out. No? But the difference between the performances of these two, the ensemble and the SVM, is going to be small, very small. Okay, which one of them is the winner? I won't tell you now. You work on it yourself. But if you do it correctly, you will notice the difference in performance between SVM, which is a very powerful classifier, is very close to that of the AdaBoost. Some more details of the AdaBoost algorithm. This is the most basic form of AdaBoost. Here, the training set of M instances will have labels -1 or +1. And the classification, well, this is the algorithm. So you have as input, you have a weak inducer, let's say a perceptron or decision tree, and then you specify the number of iterations. Then also the training set, of course, and you would want to get the output, which is your classifier. There are T of them, big T classifiers with coefficients alpha T. So you initialize your counter to 1, and then you initialize your distribution. You have a distribution here, probability distribution of choosing a sample. That would be a uniform distribution here. There are M different samples in your training set, and we repeat the following procedure. We build a classifier, empty, using the inducer, I, and distribution dt. Okay, this distribution changes from iteration to iteration, and then you solve for a quantity called epsilon sub t, and then if this epsilon is greater than 0.5, then you exit the loop. Otherwise, you continue. So you compute for alpha, which is this formula, and then you change the distribution according to this formula, and then you normalize your distribution vector to be a proper distribution, and you keep on iterating until you reach the end, which is t, big T, so that at the end you have t different classifiers. So the classification of a new instance made by voting on all classifiers empty produced here, each having a weight of alpha t, okay, alpha t there, would be the following. So that is the basic ADA boost algorithm. So this is the same data boost algorithm for the binary as a binary classifier. So similar to what we had earlier. We will go into the details of this at the end. So let's go to the next slide. Now the ADA boost improves performance accuracy for the following reasons. Well, first, it has higher accuracy because it generates a final classifier whose misclassification rate can be reduced by combining many different classifiers whose misclassification rate may be high. The misclassification rate, or the probability of it being correct, is say 51%. If you put many of them together, you can get as close as you can, arbitrarily close as you can, to 100%. Of course, you need a lot of these classifiers. So having a lot of these weak learners together can actually give you very high accuracies. Then second is lower variance. The boost produces a combined classifier whose variance is significantly lower than the variances produced by the weak base learners. However, of course, the boost sometimes fails to improve performance of the base classifier because of overfitting. So this is something that we need to remember. There's a possibility of overfitting because a large number of iterations may result in an overly complex inducer, overly complex composite classifier rather, that is significantly less accurate than a single classifier. So how do we avoid overfitting? By keeping the number of iterations as small as possible. Now let's take a look at the independent ensemble methodology this time. So the diagram on the right captures the idea of the independent ensemble methodology. So in this methodology, we have the original data set that is transformed into several data sets from which several classifiers are trained. So this is your data set, original data set. It is transformed into several data sets, 1 to up to t, from which different classifiers 1 up to t will be trained on. So the data sets created may be disjoint, meaning mutually exclusive, or it could be overlapping. Now, the combination method is applied in order to output the final classification. So this is this part here. And we can use different inducers at each data set. Meaning, we can combine You can combine inducers, meaning this could be a perceptron, this could be decision tree, you know, different inducers. It's not just all perceptrons or all decision trees, the same type of inducers. No, you can combine. And looking at this, you can actually have a parallelizable system. Okay, so here you notice that this dataset manipulator does not take in any input from any other classifier. No, so there's no input from classifier 1 or the other classifiers for the dataset manipulator. You have actually removed that arrow there before. So now this is independent and can proceed on its own independently of the others, meaning we can make this parallelized. You can parallelize the process. And this can aim either at improving the predictive power of the entire classifier or decreasing execution time. Now, earlier we were talking about the weak learner. This time we will talk about the unstable learner. The unstable learner is not the same as a weak learner. What is an unstable learner? An unstable learner is one where perturbing the learning set can cause significant changes in the constructed classifier. Meaning, you change the learning set and the constructed classifier will be totally different. That means you have an inducer that produces dramatically different results from different training sets that differ only just slightly. Example of that would be decision trees. Again, so decision tree is also a weak learner, but not all weak learners are unstable learners, nor are all unstable learners weak learners. So these are distinct concepts. Now, bagging or bootstrap aggregating creates a composite classifier I star by combining the various outputs of the learned classifiers into a single prediction in this manner. Okay. So the algorithm is the following. We have an inducer, and T again is the number of iterations, S is the training set, and mu is a subsample size that is specified by the user. And you'd like to create your classifiers empty. There are T of them, big T of them, and we just repeat the following process. First step is we sample mu instances from the training set with replacement, and we build the classifier empty using the inducer applied on your sampled data. And we increment, we keep on doing that until we have big T different classifiers. So in this case, each classifier is trained on a sample of instances taken with replacement from the training set. Then the sample size is equal to the size of the original training set. Some of the original instances of S may appear more than once in ST, and some may not be included at all. Although the training sets in ST are different from each other, they're not statistically independent. Also, to classify a new instance, each classifier returns the class prediction for the known instance. This way, the composite bag classifier I star returns the class that has been predicted most often. Now, the combined model often performs better than the single model built from the original single data. So bagging can actually eliminate the instability of unstable inducers. Now let's compare bagging and boosting. For boosting, each classifier is influenced by the performance of those that were built prior to its construction. Okay, remember the data manipulator for the second iteration is actually taking in as inputs the output, the misclassifications of the previous iteration, so that the new classifier now can pay more attention to the classification errors that were done by the previously built classifiers. That's boosting. And also for boosting, the instances are chosen with probability proportional to their weight. Okay, so there's a distribution, probability distribution, which will be used to for sampling the data set in order to produce the particular data set for that new iteration. For boosting, inducer instability is not required. Only an error rate that every classifier must be kept below 50%. Okay, so meaning it has to be better than 50% accuracy, better than random. Bagging, on the other hand, has the following: each instance is chosen with equal probability, and this requires an unstable learner as base learner. So that's bagging. For boosting, you need a weak learner. Now, having said this particular statement that each instance is chosen with equal probability, there is, however, a variant called wagging, a variant of bagging, in which each classifier is trained on the entire training set, but each instance is stochastically applied a weight. So no longer equal probability, but it's given a weight that is stochastically assigned, and that's this algorithm. It's called wagging. So it's a variant of the second type, which is wagging. Now, how do we combine classifier outputs? There are two main ways: weighing methods and meta-learning methods. We will focus on number one. The second one we'll just talk about it in passing. Weighing methods. This is the most common weighing method, the majority voting method. Here, a classification of an unlabeled instance is performed according to the class that obtains the highest number of votes. Meaning majority voting, okay? So it's just 0 or 1, vote, yes or no, and you simply count the number of votes. So anything that's above 50%, that's the winner, okay? Simple majority. Okay, so that's of course you have to write it down mathematically, but that's the idea. So the class of X is just the argmax of of the following: sum of the g of y sub k, comma ci, where this quantity here is a classification of the kth classifier, and g is an indicator function defined as follows. when the when y is equal to c, this inputs or this outputs a value of 1. So meaning, okay, so for class 1, for example, anything that if y is class 1, okay, meaning also meaning there's a match between the two, then this turns into 1. We sum up all this, and that would be the, the count all of this, put them together, and that would take the argmax. That would be the class of your instance. So for probabilistic classifier, a crisp classification can be obtained as follows. Again, the same idea, but this time the one that you measure is the argmax of the posterior. The one with the highest posterior probability, that's the class for that particular input. Then you ask each of these different classifiers, which one is their vote. Then performance weighing. Here, the weight of each classifier can be set proportional to its accuracy performance on the validation set. So you have a validation set, then you measure the performance of a particular classifier in that validation set. That would be E. E is a normalization factor based on the performance evaluation of classifier I on the validation set. Then you do that for all the validation sets. Sorry, not validation sets, all classifiers. That would be the weight of each classifier. Then you have the distribution, summation. Here, we sum up the conditional probability vector obtained from each classifier. The selected class is chosen according to the highest value in the total vector. So here again, it's like previously, this is your posterior probability. Your input is x. Now, when y is equal to class ci, okay, what is the probability of that? What is the posterior probability of that? You sum that up, then you take the argmax. That will be the class for your input x. Then you have Bayesian combination. Here, the weight associated with each classifier is the posterior probability of the classifier given the training set. Again, this time you weigh this with this quantity here, which denotes the probability that the classifier MK is correct given the training set S. So you'll have to multiply that by the probability of that particular classifier being correct given your training set S. Then Dempster-Schaeffer. So this method uses the notion of the BPA, or basic probability assignment, defined for a certain class Ci given an instance X. So the formula for the basic probability assignment is the following. Now the selected class is the one that maximizes the value of the belief function, whose formula is the following. So here you have A as this quantity here. And the more familiar naive Bayes also is used. The idea can be extended for combining classifiers. This time again we follow this formula. Finally, we have entropy weighing, where each classifier is given a weight that is inversely proportional to the entropy of its classification vector, such as this. We compute the entropy, take the entropy of its classification, take the argmax of that. That would be the basis for your classification. Meta learning, we won't talk about this much. Suffice it to say that One method involves stacking, which basically combines multiple classifiers generated by different inducers on a single dataset S. Here, the algorithm or the procedure tries to determine which classifiers are reliable and which are not. This is usually employed to combine models built by different inducers, and also aims to create a metadata set containing a tuple for each tuple in the original data set. But instead of using the original input attributes, it uses a predicted classification by the classifiers as the input attributes. And the target attribute remains as in the original training set. And then finally, a test instance is first classified by each of the different base classifiers. And the classifications are fed to a meta-level training set from which a meta-classifier is produced. Now, this meta-classifier combines the different predictions into a final one. Ensemble selection. The question that we'd like to answer here is how many and which classifiers should be included in the final ensemble. Some algorithms, such as bagging, predetermine the ensemble size by using a parameter such as the number of iterations that can be set by the user. So the number is specified by the user. So one iteration produces one classifier. That's for bagging. However, other ensemble algorithms try to determine the best size while training. So when new members are added to the ensemble, the performance of the ensemble is checked for improvement. If there is degradation of performance, the procedure stops and no new base classifiers are trained. Again, how do we select? How do we select which one should we include in the final ensemble? There are two popular selection approaches, the ranking-based methods and then the search-based methods. We'll discuss both of these briefly. Ranking-based approach. Here we rank the individual members according to a certain criterion, which we will discuss here, and then choose the top classifiers whose rank is above a certain threshold. So what are these criteria for ranking? We rank the classifiers according to the classification performance on a separate validation set, of course, and their ability to correctly classify specific classes. Another criterion is the forward stepwise selection, where we select the most relevant classifiers, maximizing the ensemble's classification performance from thousands of classifiers. Then we also look at the agreement-based ensemble selection. We don't want classifiers that are the same or very similar, even if they are high-performing. Because if you have high-performing classifiers and they're almost the same, what's the use? You just select one of them, and that's your classifier. No? So we want diversity, and to measure that, you look at agreement or of the different classifiers. So there's agreement-based ensemble selection, which uses what's called kappa statistics. So the pairs of classifiers are selected in ascending order of agreement until a desired number of ensemble classifiers is reached. Then you have search-based methods. So in here, you have a heuristic search in the space of all possible ensemble subsets that's performed while evaluating the collective merit of a candidate subset. So there's this Gaussian algorithm which uses a genetic algorithm. So each classifier is assigned a weight, initially a random value. Then genetic algorithms evolve the weights so that they can characterize to some extent the fitness of the classifiers to join the ensemble. Then finally, classifiers whose weight is less than a pre-specified threshold are removed. Then you have a variant of the Gaussian algorithm. So there's a Gaussian B, where instead of assigning a weight to each classifier, a bit is instead assigned to each classifier, indicating whether it will be included in the final ensemble. Here also, the ensembles generated are smaller in size and will have stronger generalization properties. Now let's talk about our AdaBoost example. So in order to understand the ensemble classifiers, it's best that we have a worked out example similar to the spam filter that we made. So we understood the design of the spam filter by working out a specific example. So we'll also do that here. So let's review the AdaBoost algorithm. So for AdaBoost, we're given examples S, that's your training set, and the learning algorithm L, and we define N to be the size of our training set, data set. We initialize with uniform probability distribution a vector called W. So it's a uniform distribution. There are n entries, big N entries, components of your vector here, describing the distribution. And each of these elements would have a value of 1 over n. Then we repeatedly run our learning algorithm L on training sets S sub t, which would be a subset of the entire training set to produce H1, H2 up to Hk. So H for hypothesis. Okay, what's the hypothesis? Again, there's a this is not the hypothesis that statisticians think, no? When you say hypothesis in statistics, that has a very specific meaning. So this is not at all related to that. Now think of the hypothesis term for machine learning as nothing to do with the statistical notion of hypothesis. So it's just used for historical reasons, which I will not explain. So in other words, the hypothesis for statistics is not the same as hypothesis for machine learning. So hypothesis in machine learning basically is a candidate model. That's it. It's a candidate model. So you produce candidate models H1, H2, and Hk models, you can say. At each step, we derive St from S by choosing examples probabilistically according to a probability distribution defined by our weight vector Wt. T is our iteration count. Then we use St to learn Ht, our Tth hypothesis, which will produce the Tth classifier. And at each step also we derive the probability distribution over the examples W by giving more probability to examples that were misclassified at step T. And finally, the final ensemble classifier H is a weighted sum of all the H's at each weight, with each weight being a function of the corresponding HT's error on its training set. So that's your AdaBoost algorithm. More concretely, this time using equations, we have the following. You're given a training set with data points x1, y1. That's your first data point. X1 would be a vector of features or attributes. Then y1 would be your label. So you have n, small n of these similar points, similar examples, where x here is a vector, feature vector with the elements. Y is the label, which just has two possible values, +1 or -1. We initialize our W vector to 1/n. This is our uniform distribution. Then for t equals 1, we will of course aim to produce at the end of the iteration one classifier, and we will have k classifiers at the end. For t equals 1, we select a new training set st from, or S1, from S with replacement according to W1, which in this case, this should be W1 by the way, which in this case is a uniform distribution. Then we train L on ST to obtain the hypothesis HT. We compute the training error, epsilon of t of HT on S on the entire training set. So the training error, epsilon, is just this sum of this WT, this is your vector here, times times delta, where delta is 1, it's an indicator function. When the label and the prediction of our hypothesis or our sample, our candidate classifier, our first classifier, do not match. If there's a match, 0. So basically, we're counting the number of errors, the number of times that your classifier H1 makes a mistake, because Y here is your correct label. So that would be your error, epsilon. Then we compute the coefficient alpha according to this formula. So 1/2 ln1 minus epsilon over epsilon, where epsilon is this quantity here. Then we compute the new weights for S for I equals 1 to n. Okay, n is your number of training points here. It should be big N, by the way, big N. We follow this formula. So the next value of the element of the weight distribution is equal to the present value times exponential minus alpha t, which is this quantity here, times yt, which is either 1 or -1, times the output of your classifier, divided by the normalizing factor chosen so that this remains a probability distribution. So it's this quantity here, normalizer. At the end of the kth iteration, we have hypothesis H1, H2, Hk. These are the classifiers, the k different classifiers, and coefficients alpha 1, alpha 2, up to alpha k. With this, we now have the ensemble classifier, which is a simple classifier. Basically, we multiply. You have an input x. You ask each of the different classifiers to output their results. You multiply their results by alpha t. So each one will have a particular alpha. Sum them up, check the sign. If the sign is negative, then classify it as negative 1. If the sign is positive, then classify it as positive 1. If it is 0, well, very small probability that it will have 0. But anyway, if it is exactly 0, then you just toss a coin. So it could be 0 or 1, it's up to you. So let's have a workout example. Suppose we have a training set with the following points. The first point we'll have for each label +1, okay, and x1 here is your feature vector. It's a vector, okay. It's not. It's a vector. Yes, it could be. It could be your like what you work on your spam filter. That is your vector of vector that describes your document. So it could be 30,000 dimensional vectors, but that's just x1. For x2, another document perhaps. Again, the label is 1, which probably means spam, and so on. So you have the first 4 examples. You notice that they're all ones, no? +1, and then the next 4, -1. So 4 points. The first 4 points, x1 up to x4, labels 1, while the 5th to the 8th examples have labels -1. So where here x1 up to x8 are the training feature vectors whose labels are 1, 1, 1, 1, -1, -1, -1, -1. Okay, so x1, the label is this, x8 is that, x5 is this, -1. Now, step 1, t equals 1. W1 is, how many points do we have here? 8. Therefore, we have 1/8 for each of these elements, okay? Element of your vector. 1/8 because we have a uniform distribution. This basically says that we will sample using this distribution. We sample from distribution W1, from which we get the following: x1, x2, x2, x4, x4, x5, x7, x8. Is this a valid sample? Yes. Yeah. How about x3? Well, it wasn't chosen. How about x2? It appeared here twice. Well, it was chosen twice. It's still a valid. This is a valid sample from this distribution because we're sampling with replacement. Okay, so some of this will appear twice or more than twice, and some will not even appear, like x6 here in this particular case. So this is a valid sample from this distribution. We train classifier. We have a classifier. You choose your own classifier. Decision tree, it doesn't matter for now, as long as it's a weak learner. So you train your weak learner inducer to produce a classifier in order to get H1. This is now your classifier H1. In fact, I should say inducer to produce classifier H1. Now we run the model H1, hypothesis 1, on the data set, all these, okay, this points here. And suppose the classifications are +1, -1, -1, -1, all of them -1 except for the first one. And this is a valid, it's a valid output of your first hypothesis or first candidate classifier. You'll notice that there are mistakes. Second, third, and fourth are wrong because the correct labels are this. So the ones in red are the errors. Then we calculate the errors. Okay, using this. So you just use this formula, W1, okay, for J equals 1, there's no error. So the indicator function will return a value of 0, right? Because for the first one, this is correct. Okay, the label is Y, and it matches this. Therefore, this returns a value of 0. The delta here is an indicator function will return a value 0. So doesn't matter. So this will only return a value 1 for the second, third, and fourth. And for the second, third, and fourth, W's of I are 1, 8, 1, 8, and 1, 8. And therefore, times 3. So you have 1, 8, 1, 8, plus 1, 8. 3 times 1, 8. That's 0.375. That's your epsilon of 1. Note that the error must be less than 0.5. Okay? If it is greater than 0.5, that's bad. So we reject that. Hypothesis. No, ulitin natin. No? So go back. Okay, reject. Stop and go back to this. Sample again. Run this part here until we have something that's less than 0.5. So this is less than 0.5. This is acceptable. Then we now calculate alpha. So just plug into the equation 1 minus epsilon over epsilon ln times 1/2. That's equal to 0.255. Remember this value. This is alpha 1. This is going to be very important for later. Okay, now we now go to iteration 2. And iteration 2 involves computation of the W's, because this will no longer be 1/8. This will now be, the elements will be greater than or higher for those that the candidate hypothesis made a mistake. So H1 made mistakes on the second, third, and fourth instances or samples. Therefore, W2 in the next iteration should focus on these errors. So we expect that the probability distribution will focus on this, meaning these samples 2, 3, and 4, x2, x3, and 4 should be chosen with greater probability than 1/8. So let's do that. Let's do the computation. The computation is as follows. Basically, in the numerator, we have the following. Before it was just 1/8. These are all 1/8, right? For x1, x2, x3, up to x8, they're all 1/8. Okay. Here. Okay. Then exponential minus alpha 1. What's minus alpha 1? Minus alpha 1, or alpha 1 is 0.255. So this is alpha 1 times yi h1. Okay. So for the first sample, that's correct, right? This is correct. 1 and 1 is correct. So there's error only on the second, third, and fourth, right? And on the fifth, sixth, seventh, and eighth, they're all correct as well. But you will be multiplying this and that, y and h. So which means plus times plus is plus, plus times minus is minus, also minus and also minus. And minus times minus becomes plus, and so on. So, okay, plus times plus, plus times minus, because there's a mismatch in the labels also for the third and fourth. For the fifth and up to the eighth, same labels. So when you multiply this, it's 1 positive. Also for this one. But when there are mistakes, there'll be errors. When there are errors, rather, there will be a change in sign, so negative. So now if you do the computation, this will come out, these values will come out. And then you add all these different values, that will be your normalizer. Okay, so the z here is just basically the sum of all these. And if you do the addition, it will be 9.968. That will be the normalizer here. So 0.0968 divided by z1 gives us 0.1. This divided by z1 gives us 0.167, and so on. So now we have W2. We now have a new distribution. Okay, the new distribution, as you notice, will focus more on those elements which were erroneously classified: the second, third, and fourth. So this is 10%. This is 16%. 16%. So if you sample from this distribution, you will more likely get these points x2, x3, x4 compared to the other points x1 and the rest. So let's do that. Okay, the second iteration, this will be our new distribution. We sample from this distribution, and from here we get x1, x2, 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 x3, x4, x4 also. Then so there are 8 samples here. It should be 8. And this is x5 and x7. So this is a valid sample from this distribution. Then we again train the classifier S2 on inducer S on S2 to get classifier H2. Then we run H2 on S. S is this, okay, these points here. Then we get the following classification. So this time the errors are here. Okay, the last 4 are now misclassified by the second classifier H2. So we calculate the error, same calculation as before. So this is 0.1 plus 0.1 plus 0.1 plus 0.1, or 0.1 times 4, that's 0.4. Again, error must be less than 0.5. Check, it's less than 0.5. Then we substitute this 0.4 here. Solve for alpha 2, we get 0.203. So we repeat the same computation. So similar to this, but this time applied to this results, to these results. So we expect that this will have an increase. Okay, the distribution will now focus this time on the last 4 points. Okay, let's do that. Now, so once we do the calculations, try to do this on your own. It has now increased from 0.1 to 1.125. Okay, the first one, which was correct, classified correctly by the first and second, will have a smaller chance of getting chosen for the next round. Okay, so we sample from this distribution. We get the following sample vectors, training vectors, S3. We train our inducer on S3 to get H3. We run H3 on S again, and the classifications are the following. We calculate the errors similarly. We get a 0.264. We plug in 0.264 here. We get 0.513. So now we have the following ensemble classifier. Sine of 0.255 H1. Don't forget to keep a copy of our first classifier. 0.203 H2. This is the second classifier from the second iteration. And the alpha for the third one, alpha 3 is 0.513 times H3. So this 0.255 and 0.203 are the alphas for the second and the first iterations. So 0.255 times H1, then 0.203 times H2 plus 0.513 times H3. Okay, so here we just set k equal to 3 because we're already tired of calculating. No? So we're doing this manually. So if you do this in a computer, you can have 1,000 classifiers, and it will run very fast. No? So typically you have maybe 500, you set k to 500, 1,000, it depends on the problem. So, and then you have now just a summation of all these. No? So you have 1,000 different little weak learners, each weighed by their individual alphas, and you add their results, the classification results, and if it's turning out that it's negative, then it's negative, -1. If it is positive, then it's just positive. So each of this, H1, H2, H3, and so on, will produce an output that's either 0 or 1. So, okay, 0 or 1. And then you just add them up, the result, check the sign of the result. That's the classification of your ensemble classifier. So it's really very, very simple. You can even do it by hand. So references are the following books. The first one is a very important book. So you can also refer to the second and third references for if you want to know more about today's topic.